going to talk about are really low-level things in Go. They're not even like weird. They're just, I'm talking about strings and slices today. So it doesn't have to be something fancy or amazing. Just pick something you are passionate about and start speaking. It's not as scary as it sounds, I promise. I'm a DevX engineer at Weave. That means that I write the tools for our developers. So I spend a lot of time in Go, but I'm not writing the Weave platform so much as it is I'm writing tools for developers, which is almost harder because developers are even more picky than normal customers when it comes to your tools. And like I said, I want to talk about all different types of Go level types, low-level Go types. This whole thing was born out of a bunch of questions I had when I started getting deep into Go. Now, I've been doing Go full-time for about 2 years, and I was doing it half-time maybe a year before that at my other company. And you start digging into Go, there's some of these are really obvious, simple questions, and some of them are more nuanced. I'm not going to go over each of these because we're going to cover them in the talk, but this whole thing was born out of questions and things I didn't really understand about Go and questions I had when I started writing a lot of Go code. I also want to say, I love that somebody chimed in. I've given a version of this before and I had to pre-record it. So if you have questions, let's talk about it. Interrupt me because I'm here for the live, quote unquote, live energy. So feel free to ask me questions as we go. Hopefully I'll answer them as we go along. So let's talk about bools. We're going to talk low-level types. A pretty dang simple thing to talk about is a bool. And a question that I had, and I'm going to start really simple, is how big is a Boolean, right? If you've dealt with databases, you might think, okay, well, a Boolean is a bit. It takes one bit, or a 0 or 1, a true, false, like one tiny bit of information to be on or off. So what we're going to do, and I'm going to use a lot of this unsafe.sizeof function in the talk to kind of break down the underlying memory size of things, which I find interesting when we talk about low-level types. So let's do it now. Let's declare a bool and get the size of it and print it out. And it seems like we answered our question, right? Okay, a Boolean is 1. But I want to dig further into this unsafe size of function that is built into Go, specifically that it returns the size of the thing that you give it in bytes. So you're going to see a lot of this, and I said this is a highly trivial example. We're going to see a lot of this in when it comes to other low-level types tonight. Let's actually calculate how big a bool really is in bits. Even though it only takes 1, it turns out that a Boolean in Go and a lot of languages for certain performance reasons is actually stored as a full byte of memory under the hood, even though you only need 1 of those bits. We'll come back to reasons when we talk about structs. I'll talk about alignment and why we waste so much space a lot of the time, or seemingly waste space. But it boils down to we optimize for runtime performance, not necessarily memory performance. But that's I'm going to track the interesting discoveries that I had as I was going through building this talk. And that is that Booleans are actually a full byte wide. If you've ever dealt with, like I said, databases or other languages, this may not always be true, but it's true in Go. So it's not super mind-blowing, but kind of neat. Another question I had when I started doing a lot of Go was, what's this deal with this int type and then all these sized variants of ints? And which one should I use? So I've got really trivial code here that declares and puts a 10 into 2 different types of int and then prints them out, and they seem interchangeable. And of course, we know that int64 is 64 bits wide, and that means something as far as how big the maximum numbers we can put in that variable are. But to answer my question, which one should I use? I thought I'd go to a really, really big Go project and see, well, find a really big project in Go and see what they do. And it turns out that Go is self-sustaining and written in Go, which is kind of fun. So according to the source code for Go, which is written in Go, this is the kind of rough occurrence counts I was able to generate by just parsing the code. And this may not be exactly precise, but it gave you an idea that inside Go, most of the time, they just use a plain old int. The majority of the time, they use int 8 a little bit, int 16 even less, and then more commonly the 32 and 64 variants. But I kind of took away from this, don't be afraid of the int, because Go itself thinks it's fine to use int. But I didn't answer my other question, how big is an int? Before we get there, let's prove that all these sized variants are the sizes that we expect. So I'm just making empty variables of different types and printing their sizes. And to nobody's surprise, all the sized variants of ints are exactly as big as they say they're going to be. Same thing with the uints. If I do same thing, print a bunch of variables for uints, they're all as big as they say. So let's take this same paradigm for int and uint that are unsized, and let's print out their bit size. So running this code on my machine says that int and uint are 64 bits. So we answered this question of, well, how big is an int and a uint, right? No. So that is correct for me running this code on my machine, but not technically true always. We can demonstrate this by explicitly taking the same code from before, where we just make an empty int and an empty uint and print out their size, except for when we run this code, we're going to run it with the goarch environment variable for a different architecture. And you can see that when we compile our code specifically for a smaller architecture, this same exact code reports that those two variables are actually 32 bits and not 64. And if we dig into the Go spec, which I'm going to point to a lot tonight, you can see that, yeah, according to the Go spec, int and uint, their sizes are implementation specific. So depending on exactly where you compile your code to run, those might change size and might be smaller or bigger. So to kind of come all the way around and answer my other question, which is which one do I use? Sort of conventional knowledge is that it's totally fine and safe to use the unsized basic int or uint in most of your code. And I proved that because Go itself uses that all the time. And that's totally fine. The main time you use the size models is when you're going to share data models between programs and especially between other languages, so that you're guaranteed that, you know, if you're expecting that a field could have, say, a 64-bit integer, that it's always going to have a 64-bit and it won't accidentally get cut off when you run it on a smaller architecture. So hopefully that makes sense. Again, the answers are use int most of the time, uint for, and the size variants for shared data models, and they change. So that's the takeaway here is int and uint can actually change size in Go, which I find fascinating. Moving on, I'm going to talk briefly about floats, not in depth. There's a whole thing we can cover about floats. I'm doing some very, very basic floating point math in this function. I'm taking an A and a B and adding them together and hoping that they equal C. And if you've done a lot of programming in any language, you'll know what to expect from this, and that's actually false. And I'll show you why. If we print these A, B, and C variables, and including when we add A, B, and together with more precision, so if we print more decimal places, we'll see that indeed, because of the way, and this isn't Go, this is all computers, and this is just floating point math in any language, it's got arbitrary precision. And so if you print more decimal places out, you'll see that, okay, well, actually, you know, when I add these together, I get something above 3, whereas if I declare 0.3, it actually rolls down. And I won't go into the details of this. This is, again, how all languages work. The interesting thing about how Go works with floating points is with a very tiny change. If we take those variables where the arbitrary precision caused chaos, and we turn this into a constant, it's actually going to come out to be true, which if you know computers, you wouldn't expect necessarily. And again, I'm going to print out that same code with more precision to see that indeed, when we use constants, Go in the spec says constants have a fixed precision. So even though they're floating, they're not really floating when they're constants, which means that they might behave in a different way than your variables would. And that's the big takeaway. I know that's a lot to cover, but the takeaway is that float constants can have fixed precision in Go. And even more importantly, and we'll hit this again in 2 seconds, constants and variables, just changing something from a constant to a variable or vice versa, can have unexpected side effects in Go. And that's something that absolutely tripped. I haven't hit the floating point constant issue before, but I've definitely hit the next one in real life. And I'm going to illustrate another constant problem in Go by talking about sleeping, and specifically when we do something like this. And this is code we've all written all over the place. We're going to print out that we're going to sleep for 2 seconds. We're going to actually sleep by using the time second constant and multiply it by 2, and then print done. And to nobody's surprise, that works. I wait for 2 seconds and it does it. If I move that 2 out of these 2 different places and I refactor it away into a constant in my function, the same thing works, right? It's the same code as the previous page. I've just moved that 2 from being hard-coded in 2 places to putting it in a constant in 1 place, and that works. What gets people is when you say, well, it's all fine that I can always sleep for 2 seconds, but even better, I want to pass a variable to this function that lets me sleep for some unspecified or changeable or configurable number of seconds. So we do this. We take the constant off of the front of this. I've got a lot of stuff here. If you were called this Go file, you could pass an argument. And if you give it more than one argument, it's going to take the first argument, convert it from a string into an integer, because all arguments are strings in Go, and then save it. So this is a lot of work to say, hey, sometimes this is going to, the variable content is going to change based on command line arguments. But really, the main meaningful change I've did is I've taken this from a constant to a variable. And if I run the same code, leaving the rest of this the same, this happens. And this happened to me in real life the very first time I started dealing with a lot of configurable sleeps. And you get this problem where you say, okay, well, I get mismatched types between time duration and int. And I'm going to actually focus in on that. So other than the command line parsing, I changed one thing. I took the constant off and made sleep seconds a variable. How did that break my code? To understand that, we have to understand what constants are in Go, and what the type of constants are in Go. And it turns out that most constants in Go are not typed, which is really weird because Go is a strictly typed language, except for its constants, which are a lot more wishy-washy. And kind of the compiler does a lot of magic under the hood. I'm not going to read the full thing here, but I want you to take away that constants in Go usually don't have a type at all and just kind of are coerced into what they need to be at any given moment. So to show you that, essentially, when we use a constant in our code like we did originally, the compiler and Go, right before it compiles our code, effectively rewrites it and puts this little conversion. It says, well, I know that a 2, an untyped integer constant of 2, can actually be converted to a time.duration. So I'm going to silently do that conversion in your code before I compile it. So this happens behind the scenes. You never see it, but this is effectively what's happening. So when we want to turn our variable, which can't be wishy-washy and has to be typed, when we turn to a variable, we have to actually start doing that conversion ourselves. We say, okay, well, here's the sleep seconds is now a variable. I need to explicitly convert it to a time.duration before I multiply it by another time.duration. Also fun, these 3 string constants are still technically untyped. There's sort of kind of half typed in that they're strings, but they're what Go calls an untyped string constant. But if I do this time.duration conversion and wrap it around and say, okay, I know you think it's an int, but it really can be a duration, and we do what the compiler would do for us, we can make this code work. So the main takeaway is that constants can and usually are untyped. And you often have to do those conversions yourself. And another thing, like I said, same thing with floats. Just going from variable to constant can change how your code behaves entirely in Go, which is, I think, interesting. A little scary sometimes, but really interesting. Let's move on next to IOTA. And someone tell me if I'm going too fast. I've got a lot, and so I'm trying to make sure I get everything covered. We see this a lot in our Go code. We have a constant block. We say that some named constant is equal to iota. Often we don't even follow it up with more equals iotas. You just have new lines. And this works. This is absolutely common Go code. We can even print those constants and see what they become to try to maybe guess what is iota, right? It's not an int, it's not a uint, it's not a string. Like, what is iota? And it looks like when you print them that iota is some sort of number. And if you dig in, okay, it turns out that yes, iota isn't really a type at all, but I was confused, which is why it's in this talk about types. Is like, is iota a type? It actually is an integer constant. And what that means is, I'm gonna actually skip to the next one. It's effectively like this. When we use iota in our code, it's effectively the compiler rewriting our code to replace every time we use the word iota with a successive untyped integer constant. So it's just like if we comment out these iotas and we put in 0, 1, 2, 3. That also means, I'm going to step back one slide. That also means that when we use iota in this way, we can actually jam an iota into multiple constants types. So here's an untyped a constant. Here's a int64b, a float64, or even a complex, there's a lot of code here where it's effectively me just going through and printing the value and then the type of each of these constants. So you can see that, yep, IOTA doesn't have a type. In fact, it can kind of be jammed into any type that's necessary when you use it. So like I said, it's effectively the compiler rewriting it, which is cool because it's an untyped constant and not really a type itself, you can actually do really weird things. I'm not sure why you would ever do these, but you can put it into an expression. Because remember, this iota is going to be replaced with a 0. This iota and this one will both be replaced with a 1. We can actually skip iotas and move to the next one, which would be replaced with a 3. So if I run these, you'll actually see that we got 0 times 2, 1 plus 1, and then 3 times 1002. So you don't often see iota used multiple times in a constant declaration, with one major exception. When you're dealing with bitwise operations and you're trying to declare an important bit and the mask that is required to fetch that bit out of your data, which most of us almost never do because it's really kind of an old school thing. But if you're dealing with network operations or really, really highly efficient operations where you use a lot of bitwise operations, you might see iota there. But the takeaway is that iota is not a type, it's a dynamic constant. And it changes value on every single line, which is pretty cool. I also want to bring up one last thing about this bit of code, is that you can use GoGenerate, this special markup in your code, and the stringer command, which is easy enough to install if you look up the GoGenerate stringer, and essentially say, well, I've got a special state type that's an int. I'm going to declare a bunch of constants that are of that type, and then I run GoGenerate. And GoGenerate, based on this command, will actually find all the uses of type state and create string, automatic free string representation. So this is the only code that I write, but GoGenerate writes enough code that when I actually start printing these out, instead of getting those meaningless 0, 1, 2, 3s, I get the actual constant name from the code put into my code at runtime from the generator. So the stringer generator can do a lot more than that, but it's really, really nice if you're doing a lot of these iota blocks to get just free, nice, printable, human readable names. Okay, so hopefully I haven't lost anybody yet. Someone speak up if I'm going too fast or I've lost you. We're going to dig more into more complex types now, starting with arrays and slices and then building on that. Arrays in Go we use basically never directly. So arrays have to have a fixed size, and when you declare them, they take up that much size in memory immediately. So if I make an array of 50 bools, then it's going to take up 50 bytes worth of space because we know a bool is a byte. And I'm just proving here that you can index it and modify an array. It's not interesting necessarily, but understand that arrays, they take up that space whether you're using it or not. And I had a question about arrays and copies. So if I copy an array, what happens? And this will be especially important when we get to slices later. So I'm declaring an array of 3 bools. I'm then copying that array to a new one, modifying my copy, and printing the 2. And this behaves in one way, and slices behave entirely differently. So if I print this out, you'll see that my original array remains unchanged, and my copy is indeed a true copy. And when I mess with it, I don't mess with my original, which means that if I pass an array from one function to another, all passing in Go is done by copy, by shallow copy. So I can safely pass arrays around and not manipulate the original. I'm going to come back to this exact code later with slices and show you how it behaves in the opposite way. So let's talk about slices and why that is. Slices are really what we use in Go all the time. And I had this question about, okay, well, if we're talking about low-level types, I kind of want to talk about slices. And it turns out that they're not really an actual type in Go. Slices are sort of a dynamically generated type, where the compiler, when you build your code, looks through all your uses of slices and builds you a bunch of custom slice structs that are what we call a slice header. So every slice you instantiate, the compiler says, well, I'm going to need to build a struct for that and wrap your slice usage in these helper functions. And that's important because when you pass slices, it's effectively the same thing as passing a struct. So you actually don't pass the underlying data, but you pass this header around. And I'll show you what I mean by that. Because this was the question I had. When I pass a slice, if I have a slice with 1,000 items in it, is it taking a lot of time to copy 1,000 items, or is it passing just a little bit? So I'm going to prove this out by making a small slice with nothing in it, and I'm going to print how big that header is. Remember, this is the slice header, not the underlying array. I'm then going to dig in and say, okay, well, actually, and I have to step back. I skipped this. Part of the slice, when we make a slice, what happens on creation of that is that it allocates a certain size underlying array for us, and then allows us to use up some part of that array until it's full, and then it allocates more. I won't go into the deep because slices and arrays are a whole talk on themselves, but there is this kind of slice wrapper and then the underlying array that takes up whatever space it takes up based on the current size of the slice. So that's what I'm getting here. I'm printing the header of the slice and how big the underlying array is. And then I'm making a slice of 100 items pre-allocated and printing the header size and the size of the underlying array. And you can see that from my small slice with nothing in it, the header is 24 bytes, which makes sense because we have 3 things in there that are each 8 bytes wide. And the underlying array is 0 to start. But with my large slice, the header is still 24, but the underlying array is pre-allocated to 100 bytes worth of memory. So to answer my question that I'm posing here at the top, no matter how big your slice is, you're always passing 24 bytes of memory. And more importantly, you're always passing a shallow copy of that slice. So if we run this same code that I had about arrays, where we make a slice, notice there's no 3 in here. That's the only difference in this code, is that I'm not creating an array because there's no fixed size of this variable. So this is a slice, which allocates that whole header that I showed you. I'm making a copy, which just copies that struct. This is just like making a struct copy. It just doesn't look like it. Then I'm going to modify my copy and print both. And you'll see that my slice and my slice copy are now changed. And this is a big got you and go, that when you're passing slices to functions, those functions are 100% capable of messing with your slice. That's just how they work. The same thing with maps, and we'll kind of get there. But be careful when you're passing slices around, because while it's great that it's efficient and you only pass a little bit of data, no matter how big the slice is, you are passing them a pointer to your data and they can just mess with it. So if you need copies, make sure you have to make explicit copies. And I'm not going to cover that, but it's pretty easy to Google how to copy a slice and go.
Can you go back a bit to the previous slide?
Sure.
So here you're showing the capacity of the, okay, I was a bit surprised that it ended up being 100, because like, I think it does tend to pre-allocate a bit more, depending on the slice. So if you append to the slice, you can end up with like, you know, the underlying array is no longer big enough, so then it has to enlarge it. And it does this kind of preemptive enlarge, but I'm not sure exactly what the factor is.
Yeah, you're right. And that's, like I said, there's definitely a whole talk we could have about slices, because you're absolutely correct that when you append to slices, if you run out of space, it makes a new array, copies everything from your old array to the new one, and it replaces the pointer. And you're right, in a lot of, when you do the make function like this, it tends to allocate exactly what you ask. But when you do appends, that's when you start getting like buffer capacity ahead of your current slice.
Yeah, thanks.
No, yeah, you're exactly right. And if I had more time, we could just talk all day about how that works, because I think that's also really fun. So the takeaway there is all slice variables cost the same to shallow copy, but they are shallow copies, meaning whoever you give it to can mess with your data, whether they mean to or not. Next, let's talk about bytes. We're going to go even lower level. So low level types in Go, we're talking about a byte, which it turns out that byte is just an alias to a uint 8, which makes sense because you just need 8 bits to represent a byte. So they're really, one is just an alias on top of the other. One fun thing about bytes and a lot of other constants and variables in Go is that Go code has a lot of notations that we don't take advantage of, I don't think. So there's integer notation, there's hex, there's rune notation. You can use underscores in your literals. So if you're building really big numbers, this can be really helpful to kind of replace where we normally put commas. Or you can use, of course, binary notation. So this code is really simple, just making a bunch of different bytes and then printing them out. And you'll see that no matter how I instantiate them, the default way that Go prints a byte is the way it prints a uint8, which is just the decimal representation of that byte. We don't use bytes a lot, but I wanted to cover them real quick because we're going to talk a lot about them when it comes to the other Go types. So when we talk about byte slices, strings, and runes, which all kind of are intermixed and related to each other. Byte slices are the thing that we deal with most often when talking about low-level operations, right? So if you've ever read files or dealt with JSON marshalling or done network calls, byte slices in just a series of bytes is the lowest level operation you can get. So you see this a lot, and there's reasons you would use this over a string. So we'll get there in a second. But byte slices are also technically the data type that is underneath runes and strings, or can be underneath runes. Runes are actually slightly different. So that's what a byte slice is. I'm going to cover it more when we talk about strings. Is there a question? Okay. So strings really are custom modified byte slices. And I think this is really interesting. So if we create a variable string that has high in it and we print out the size, and then we convert that string to a byte slice and print out its size, you're going to see that they're actually different. And I'll show you why on the next slide. Our string size is 16 and our byte slice size is 24. And that is because, and that's not even fully true. We'll dig into the actual full size, but just for the string header, it's essentially a shortened and modified version of our slice header from before. So strings are slice byte, which means our header is sort of like a slice byte header, except strings are immutable. Because strings cannot change in Go, there's no reason to track the capacity because the length is always the capacity is always the length. Both of those are identical and have to be all the time, which is why we got 16 for our string header, 2 8s, and 24 for our byte slice header. But the question is, how big is, and I've had this working on Go, like, how big is this string really under the hood? Because if we just run the size of, I don't really get the actual size. What I have to do is declare my string, get the size of the header for the string, then count the number of bytes inside of it, which is easy to do by just getting the length. And then I'm going to add those together. And I'm going to do the exact same code, but with slice, except I'm using capacity because my slice has some extra capacity that is allocated on top, like we just talked about. So the true size of my string is the size of the header plus the actual content of number of bytes in the string. So for my string, it was 18. And for my byte slice, just high, I literally converted the same string to a byte slice, actually ballooned up to 56 bytes of memory. Be wary about worrying too much about those headers, by the way. Strings are more efficient in a lot of ways, except for one big way. And that is, it's 2 slides down. That is string concatenation. So we'll get there in a second, but understanding that strings are, in a lot of ways, when you pass them around, you're only ever passing 16 bytes of memory, and that's pretty small compared to the 24 that it would take to pass a byte slice around. And definitely under the hood, they actually take up less overall for small cases. I'm actually going to skip. Well, we'll cover this. So another question I had is what happens when I append, when I convert my string into a slice byte? It does become modifiable, but it makes a copy. So talking about slices and array copies, if we make our original string, we convert it to a slice byte, we modify that slice. I'm going to change a character, and then I'm going to append a bunch of bytes onto the end of it, which I don't know why you would do it this way, but you could. And I want to prove that this is actually a copy operation, and strings really are immutable even if you convert them to another type. So you can see that even though I messed with my copy and even put an emoji in there, and I'll show you how that got there, I didn't actually change my strings. Really are immutable, even if you try to mess with them using kind of type manipulations. So to summarize, strings immutable, they have less overhead. They can be constant, which is a big difference. Byte slices of any kind can't be constant. They have to be variable. But because they're immutable, when you add 2 strings together, Go copies the content of both of them to a third location, meaning that do not use string concatenation to build a big string. Don't go string plus something plus something plus something, because every single time you have to recopy the entire content of both things to a third place. So that's a use case for using a slice byte, or even better, use the strings builder interface, where it has some helper methods that use a byte slice under the hood for efficient concatenation, but let you just get it out in a string when you're done. Slice bytes are, like I said, they're super low level. They can be modified and appended without doing a bunch of copies all the time. But they have a little bit more overhead. You saw how much bigger our small string got. And you kind of, the takeaway is use them where they're appropriate, but they are semi-interchangeable. We're going to move on. I'm going to talk about string indexing and some gotchas that hit me when I was dealing with strings. So we know that strings are byte slices, which means I can index a string. I can say, okay, well, I've got this very simple string, and I'm going to take item 3 out of it, which is 0, 1, 2, 3. So it should be an M. I'm going to print out what's at index 3. I'm going to print out the type of the thing at index 3, and then convert it to a string and print it a second time, and you'll see why. So when I take, and this got me big time when I was doing a lot of Go early on, like, why is the third thing from my string not a character? Where does this number coming from? Well, it's from the actual byte at index 3 in that slice. So it's not a string. You see that's uint 8, which if I convert it to a string is my M. So you'll see a lot of times, you'll print what you're thinking is a character, and you actually get some random number, and it's because that's what you pull out of a string by default. It can also lead to really nuanced bugs. String indexing works okay, and converting it to string works okay, until you have some extra character that's non-ASCII. So this is the same code. I just changed this A. Let's run it and see that, okay, well, now at index 3, it's 161, still uint 8, but it's an upside down exclamation mark, which isn't even in my string. So you can get really confused now and go, okay, well, now how did that? That's not even close to what I wanted. And the main reason is that non-ASCII characters can be made up of multiple bytes. So if I'm take that string, convert it to a byte slice, I'm going to print that slice out, show you what index 3 is, and then print it out. And I'm going to do the same thing for my second string. So this is a lot of stuff to just print these strings as byte slices and then print their individual items to show you what's happening under the hood. So the first byte of both of these strings is 73, which is an ASCII capital I. Then we have 32, which is a space. Then the next one for my first string is 97, which is my regular A. But for my other string with an accent mark, I actually got 2 bytes in there, because a 195 plus a 161 is an A with an accent. But if I just index that third item, that's how I got 161 and not my original item. So how do we fix this? How do we deal with strings that have weird characters in them? And it turns out that runes are the answer. They're still not 100% rock solid, and I'll show you how you can even break a rune slice. But let's talk about runes before we go on to that. Runes are the default type that are created when you use your fuzzy constants. So if you've ever tried to use single quotes in Go and put a whole string in there and got yelled at, that's why, because Go wants you to have one character. Character is the wrong term. Technically, it's what they call a Unicode code point, but you can think of it like a character. They're an alias to an int 32. And you can just declare them inline, including, I really blew a coworker's mind by just pasting an emoji into my source code once. And now we have it all over in our source code. We use emoji like crazy in our developer tools. And Go will happily print those out, sort of.
Do you put them in Git commits as well? Mm-hmm. Nice.
Yep. Anything that's UTF-8 compatible will happily just, and sometimes it doesn't, your browser or whatever doesn't know what to do with really kind of out there emojis, but most of the time it'll show up just fine. If I print these, I do get something weird though, unless you kind of look at this. Remember, our runes are int 32s, so if I print them by default as runes, you just get the int 32 version of them. But if I string them, I can print them back out. So that's something to be aware of, that if you're dealing with runes and you want to actually see the rune in your text version, your printable version, you should string them first. We can also take these runes and convert them to a byte slice. So we string them, then we convert them to a byte slice, which isn't super meaningful, but you can see what I mean when I say that strings are byte slices under the hood. So you can take a string and break it into runes, or you can take a string and break it into byte slice, which is because you can easily take your one int32 and turn it into 4 int8s. And you don't deal with this a lot other than when you start getting weird numbers. This is the one that get me, or the original one here. This got me big time. Like, I'm looping through my runes. Why am I seeing numbers and not characters? So let's go back around to our original indexing problem. I'm going to run it again to prove, again, this was our problem. I'm not getting the characters I expect anymore. So how do I index a string correctly? And the answer is almost all the time you can go away by just converting my string into a slice of runes, right? So saying, take the string, break it up into individual printable characters or code points. And now when I get index 3, it's going to happily skip past that A with an accent because it's going to treat that as one rune, and I'm going to get my M back like I expected. And that's, like I said, this is safe 99% of the time. It's not 100% safe, and I'm going to show you how you break this. So strings are byte slices, and not all bytes show up even in a print. So I'm going to build a byte slice with the start of my original sentence. Then I'm going to append onto that slice using the hex or the notation here, a null byte, meaning nothing, which has no visual representation by default. And then I'm going to put my M on there, and then I'm going to build my final string. And I'm going to print that string. And what we will see is the I a string printed here. Then I'm going to use my perfectly sound logic of, well, convert this to a slice rune first, and then indexing is safe. And prove that even then, in especially weird cases, it might not be true. So my string looks perfect when I print it. But at index 3, which is right here, I put this null byte, which doesn't get printed because there's nothing to print, but it absolutely will index it. So you won't hit this most of the time because most things don't even let null bytes happen, but it is technically possible to construct weird malformed strings in Go and break even your rune indexing.
And does the length still work, or that breaks as well?
No, the link should absolutely work. I wish I'd left more of these with an edit.
Oh, that's okay if it works.
So yeah, but you can absolutely still do a length, and it'll show that extra rune is going to count towards the length. So it would be the number of these characters plus 2 for the accent A plus that extra byte. This also will hit you with string looping if you try to do an old school style for loop and iterate over a string. What it'll do is iterate over, especially when you've got foreign characters here, or non-simple ASCII characters. You'll see that I'm iterating through that. Not only do I have more iterations than it looks like I have characters, but I got a bunch of things that aren't even close to what's in my original string. To properly iterate, you have a string, you have two choices. You can cast it to a rune, a slice of runes first, which, like we did for indexing, this is kind of sort of the magic. And if I do that, I indeed iterate over each of those as an individual code point or rune. Or I don't know why you'd use the other for loop, to be honest, ever, but use range, because range knows how to automatically iterate a string for you without any casting. Range knows, oh, this is a string. You probably want to iterate by runes. I'm going to just do that.
If you want to modify them inside the loop, then you can't use range.
Correct. You're right. But it's a string, so you wouldn't be able to modify it anyway.
Yeah, that's true as well.
Yep. But you're right. There are reasons to use the old school loop. And if you do, convert it to a slice rune first, which you actually could modify that and then put it back into a string if you wanted. So you're right. If you wanted to like get in, and there's a lot of helpers in the standard library for like very cleanly and reliably finding positions of characters and dealing with non-ASCII characters. But slice rune is usually good enough for most of us, or just use range. Also point out that if I do this kind of convoluted thing to build that same string with this null byte in the middle, range knows how to handle that. I'll still see that null byte in the iteration. It gets an iteration and has no printable form, but you can actually, this might be a way you would detect like a really weird string indexing problem, is by iterating over those runes and saying like, oh, here, somebody stuck a null byte in my in my string, and that's why I'm getting weird indexing problems. So again, range is pretty smart. So be careful when you're indexing looping a string, and definitely look into some of the helpers that are in the strings package that let you do better and more intelligent searching of strings.
Just curious, do you have any sense of, does range automatically convert that to runes, or is it just doing a whole bunch of compiler magic to figure out what the right thing to do is there?
I think it just converts it to runes before it loops. I have no idea though.
Okay, just curious. Thank you.
Yeah. So next, let's talk about structs real quick. There's nothing super surprising about structs when it comes to Go, except for when we talk about empty structs, and we'll get there. So structs in Go, we use them all the time. They can have 0 to any number of fields. Structs are usually, but not always, as big as just their constituent. There's no struct header. So if I make a struct of data, it's only going to be as big as the size of X plus the size of Y. And I'm going to prove that in this code that, yep, the size of X and the size of Y is equal to the actual size of the struct. This gets a bit weird if you have pointers and if you have maps and stuff, but as long as you're using simple types, this is pretty easy to prove out.
I think it might do padding in some cases if you don't have word alignment.
You're exactly right. And you're beating me to it. I'm going to jump to that slide. So you're right. Definitely not always. Go, so if I change my 32 and I go from 4 bytes in the first one to 8, I'm glad you talked. That's awesome. You're right. It's still 16, which is a bit weird.
Plus talking, you know.
Yep. And if you go into the spec, and this is not just Go does this, tons of languages do this. They want your memory to be naturally aligned and to fit word boundaries, right? So it's sort of another compiler rewrite when it says, well, okay, you only took 4 bytes here. I really want things to be 8 in this case. So I'm going to just put an unused array of 4 bytes in between these two items to make things line up neatly, which is how we got that 16 in the previous code. So yeah, I'm glad you brought that up, because that'll get you. And the real thing that gets you, most of us don't have to think about this. I'm going to skip to the next thing. Well, we'll get there. So I got sidetracked a little bit. They take up the size of their fields. Even when you do nested, it only ever takes up the size of all the constituent items. Again, there's no struct header. So structs themselves don't cost anything extra. Moving on to the spec, like I said, it rewrites to do alignment. If I change this, so both of these are now 4 bytes, and I hit that nice 8-byte alignment, then it doesn't pad it anymore. I can see a padding with bools. So I know my bool takes 1 byte. And so I might think I'm saving a lot of space in my struct by using a bool instead of something else, but it's still going to always try to fill out. If I run this code, it's going to always try to fill out to that word boundary, like we just talked about. And what this really can get you is when you do packing or not. So if I stick 2 Booleans in here, it just converts this what used to be a 7 size array of bytes. So if I get the size of this, I put 2 bools in there and it's 16. So my previous data struct that only had 1 bool took 16 bytes of memory. My next data struct that has 2 Booleans took 16 bytes of memory. So it's a little weird that I can track more data in my struct, but not cost anything extra in memory, which is kind of fun. But if you do this weird, it can actually bite you. So I have the same 3 struct members, but now I've put a Boolean, then a uint64, then another Boolean. And what that means is that Go is going to put 2 paddings in here. And the actual final size that I get for 10 bytes worth of data is 25 bytes worth of memory used. This is fun. I love this. I don't think most of us should think about this most of the time. Put your fields in your struct where they make sense, unless you're building a struct that really has a Boolean and int and a Boolean and int. Like, these small things are not worth the memory save to make them more confusing in your code. Unless you're doing real low level network code, don't worry about this kind of packing stuff. But it's neat to know that literally just shuffling a line of code can change my memory footprint pretty radically. I went from 16 to 24 bytes memory used just by moving one thing in my struct. So there are Go static analysis tools that help you find these kind of problems and fix them and say like, hey, if you reorder this struct, it's going to get more efficient. So don't worry about this yourself. Run those tools if you really think you need to care about memory in that level of detail. And if you really get far, then you'll deal with like bitwise operations instead of even using Booleans. Again, most of us shouldn't care and should just write readable code first. So what about empty struct? I already said there's no struct header. So how big is an empty struct? Let's print it out.
0.
Yes. And I love this. This is one of my favorite tricky Go things in the world because it has very meaningful impacts in a couple places. Even if I take a struct and I fill it with empty structs, it still takes 0 space. Like, so I can make a struct with 1,000 nested empty structs and it still takes up 0 bytes of memory. I'm going to create an array of 100 empty structs, 0 bytes of memory. I'm going to create a slice of 100 empty structs. Okay, it's actually 24 because my slice header had to get created even though its underlying array is empty, the slice header still exists, which is a fun nuance. Again, you wouldn't deal with this much. The one place I really, really stress using empty structs, or 2 places. First, use empty structs in channels when you have a Go channel that exists purely for signaling. A Boolean can be true or false, and anyone reading your code has to think for a second, does the value coming from this Boolean channel matter? Because it can be 2 things. A channel of empty structs literally can't do anything but essentially ping you. Like there is no content, there is no value. And so it signals to the reader that, hey, when I'm reading from done, I don't even need to store this because nobody cares because it can't have a value. Equally, if you're using maps to get sort of easy deduplication of strings, which we all kind of cheat and do sometimes where we use maps to make string sets, using a slice or using a map of string to empty struct can actually save you 8 bits of memory per entry. So my other favorite place to use this is when I'm generating unique sets of strings with a map. Don't use a Boolean because that's 8 bits, a whole byte every time, but use empty struct because the value takes up no space in memory. So if you see this a lot, the double brace invocation throws people off a bit, but you're defining an empty struct and then making an instance of it. And again, the main thing is your consumer doesn't have to wonder what the value means because there is no value. So structs have no overhead, but may have padding. Moving on to maps, this is really brief and I'm kind of coming up towards the end here. Maps aren't a Go type, just like slices aren't a Go type. And they're so complicated that I'm not going to dig into them much here. Maps are, there's a whole talk about maps, but essentially it's just like with our slices. We declare maps, Go creates a bunch of map structs for us on the back end and rewrites all of our map usage into these runtime method calls with those created types. There's a whole talk on this. The one thing I will say is because maps are effectively structs under the hood when they're compiled, just like slices, maps are always passed by shallow copy, meaning if you give a slice to a function, it can mess with your slice. If you give a map to a function, it can mess with your map. Whether it means to or not, you're only just giving it just that shallow pointer to your data, but not a copy, not a full deep copy of the data, which I've seen by people.
And that's how you get a map that is nil, that is not really nil.
Yeah, and that's another. I actually have that. I don't have that for maps. I do have the nil interface problem, which is the same thing. So I'm glad you pointed it out, and it can happen with maps too. And if you don't know what I'm talking about, I'll cover that in a second when I talk about interfaces. So, and specifically nils. So interfaces, all interfaces, regardless of what's behind them, take up two words worth of data. So a uint pointer that points to the information about what's in the interface, and then another pointer that points to the actual data behind it. So if I've got a pointer to a slice, it's a certain size. If I've got a pointer to a string, it's the same size. And I'll actually demonstrate that here in a second. So I've got a function that takes a message and an interface, and then it prints how big it prints the message telling you what kind of thing you gave it, just to make it more the output human readable, prints the thing itself, shows you the size of the interface and the type you gave it. So I'm going to call this and say, well, how big is a Boolean interface? How big is an untyped constant interface, etc. And you'll see that. So for my Boolean, which we know is 1 byte of data under the hood, the interface, the pointer to a Boolean, when you pass it as an interface, is actually 16. Same thing with our untyped const, our int32, our int64. No matter how big or what we passed to the interface itself always takes up 16 bytes worth of memory because it needs to point to 2 potential places, like what kind of data did I just give you and where is that data? And you can see that I'm doing sizes of the underlying types here to see that, okay, yeah, the interface doesn't change, but the underlying thing could be any size, which is interesting because it means that when you pass things as interfaces or they're received as interfaces, you're not passing a lot of data, no matter how big the thing is, and you're never passing a copy. This is the one we just talked about. Interface nil is not a nil. And this is super weird, and you mostly hit it when you're writing unit tests. So I'm creating an x of our x, which is a pointer to an int, and then of our y, which is an empty interface, which defaults to nil. I'm going to compare each of these to nil. Oh, and this code is, sorry, man, I need to edit that. This code actually still has that typo. And then compare them to each other to prove that they actually, it's the typo, the code works the same. X is nil, Y is nil, but the X nil and the Y nil are actually 2 different kinds of nils, which is really confusing when you print them because they'll both print as nil. You see this also with maps and slices. When you're doing unit tests and your function returns an empty slice or an initialized but empty map, and you're checking for nil. And those are very different things, right? Like if I'm passing you nothing versus a pointer to nothing, those are different, and they kind of bite you in your unit tests. And I won't go into the nuances of that, but understand that, and it can be really mind-numbing when you're writing unit tests, like nil is not equal to nil, and you have to tear your hair out trying to figure out why those 2 things somehow aren't the same. So that's the takeaway. Nil interface, map, and slice nils aren't always nils, even if they print like them. So that's it. Hopefully I didn't go too fast. Like I said, I wanted to cover everything, and there's a lot of content in here. I use GoPresent to do all this, and I also wrote a nice little wrapper. So if you use VS Code and you write a lot of GoPresent presentations, I kind of have a custom plugin for VS Code that lets you control click and like edit your 10,000 Go code files from your presentations view. But that's it. If you want to, like I said, this is the second time again this talk, so it's still stored at this Go West. All the source code, the whole talk, everything, you can pull it down, you can run GoPresent yourself and actually click through and do all of this on your local and edit it and do all you want. That's all on GitHub. Like I said, I work for Weave. You can find me at Carson_ops. And if you want to interview at Weave and be a full-time Go engineer, we're looking for those. And thank you.
Hey, thank you, Carson. That was awesome, and I really appreciate it. Really enjoyed the talk, and I want to just leave it open for a few more minutes just to see if anyone has any questions. Anyone have any questions they did not ask?
Hopefully if that was over anybody's head, please let me know. I tried to keep it simple enough, but also interesting. And like I said, a lot of that is, some of that's fun nuance, and some of that's real practical problems. So Jay Frank.
Actually,